Hello guys, welcome to today's class. In today's class, we'll be discussing the concept of indices. And if this is your first time seeing my video, do it to follow through to the end of this class. And if you enjoy the class, do it to like and subscribe so you get notifications when I upload new videos. Now let's come back to the concept of indices. What is indices? Now simply put, indices is the plural of the word index. Now what now is index? If I have a given number, say a raised to the power n, this n here is what we call the index. This n is called the index. We can also call it the power. We can also call it the exponent. So why the a is called the base number, or the base, simply called the base. So the word index is simply the power to which a number is raised to. Simply put, we can say the index is the number of times a number multiplies itself. So this expression a to the power of n simply tells you that a multiplies itself n number of times. Let's give a practical illustration of this. So if I have a number 2 to the power of 3, this simply means that 2 multiplies itself 3 times. That's what the word index means. The number of times a number multiplies itself. So the expression 2 to the power of 3 means 2 times 2 times 2. That is the meaning of the concept of index. The number of times a number multiplies itself. Okay. Now, there are several operations we can carry out between two index number. Remember, so if I have another term, let's say 2 to the power of 4, because I have an index here, we can now say indices. So the operation I carry out between two index number are being governed by certain rules or laws, which we call the laws of indices. So we'll be moving over to the laws of indices, so we can learn how to carry out operation between two index number, or even between an index number. What are the laws of indices? Follow through as we go into the laws of indices. The first law of indices we want to discuss is the multiplication law of indices. Now, what is the multiplication law of indices? Let's say we have an index number a to the power of n multiplied by another index number a to the power of n. The law of indices here says that if you have two index number with the same base, you take one of the base and add the powers. So if you have an index number here where they have the same base, but the powers, whatever the powers are, but they have the same base and they are being multiplied, you take one of the base and add the powers. Okay, let's look at a practical example here. If I have a to the power of 3 times a to the power of 2, this means this will give us a, because they have the same base and they are being multiplied. You must pay attention to the operator here. As long as it is multiplication, we are using the multiplication law of indices, and you must be sure they have the same base. I know you might be wondering, what if they have different base? We'll get to that concept. When they have different base, what you do. But for now, let's pay attention to when they have the same base and they are being multiplied. You take one of the base and add the power. So this will be 3 plus 2, and this gives you a to the power of 5. Yes, and this is true because if we bring out this number, say a to the power of 3 times a to the power of 2, a to the power of 3, like we earlier explained, means a times a times a multiplying itself 3 times. Now, times a to the power of 2 is a times a. Now, if I count the number of a's here multiplied, we'll have 1, 2, 3, 4, 5. So this is a to the power of 5, which is still the same as this. So this is correct. This rule is correct. So whenever you have two index number multiplied, they have the same base, the law of indices there says you take one of the base and add the powers. Let's look at another example under this. If I have say 2 to the power of 2 times 2 to the power of 3, according to the law of indices, fine, they have the same base. The operator between them is multiplication. So we definitely obey the multiplication law of indices. We take one of the base and add the powers. And this gives you 2 to the power of 5. And this is correct because if we want to simplify this further, okay, let's just simplify this further. This is 2 to the power of 2 is 4 times 2 to the power of 3 is 8. 2 times 2, 4 times 2, 8. So we have 4 times 8. And this gives us 32. And if we want to simplify this, this is 2 times 2 times 2 times 2 times 2. 2 times 2. We want to prove that this is correct, comparing to 2 raised to power 5. Now 2 times 2 is 4, times 2, 8, times 2, 16, times 2, 32. So this and this are correct. So the law of indices in terms of multiplication holds, and it is correct. The next law of indices we want to discuss is the division law of indices. Let's say we have an expression a to the power of m divided by a to the power of n. I can also write this as a to power m divided by a to power n. It's still the same thing. Okay. So, but let me just keep it this way. If I have a to the power of m divided by a to the power of n, as long as the operator between them is division, the law of indices says that you take one of the base. Remember, the base must be the same. You take one of the base, subtract the powers. In multiplication law, because it is multiplication, we use addition. Division is the inverse of multiplication. So the operator here will also be the inverse of addition. So we have a negative, which is the inverse of addition. Okay, so this is the law. A to the power of m divided by a to the power of n. They have the same base. You are dividing. You take one of the base, you subtract the powers, m minus n. Not n minus this. This is not n minus m. This is not equal to this. Okay, so it's definitely this one minus this. Let's look at some examples here. If I have a to power 5 divided by a to power 2, according to the law of indices, we said take one of the base, subtract the powers, 5 minus 2, and this gives you a to the power of 3. This is practically correct because if you want to split this out, if you have a to the power of 5 divided by a to the power of 2, this is a times a times a times a times a divided by a times a. And if we strike out 2 of this, we'll be left with a times a times a, which is a to the power of 3. And this corresponds with this. So the law of indices on division holds that when you have the same base, you have 2 index number of the same base and they are divided, you take one of the base and subtract the powers. Let's go over to the next law of indices. The next law of indices we want to discuss is the power law of indices. Let's say you have an index number a to the power of m raised to another power again to the power of n. This is index already. Now all raised to another index again. The law of indices here is the power law, which says that when you have an expression like this, the 2 powers or the 2 index or the indices multiply. So we have a m times n. So this is called the power law of indices. If you have an index number a to the power of m raised to the power of n, that these 2 powers multiply. Let's look at some examples here. If I have 2 to the power of 3 or raised to the power of 4, this is simply 2, 3 times 4, 3 times 4, which is 2 to the power of 12. Now in indexes, it's very much allowed to keep your final expression in index form. You mustn't resolve this to a whole number or to the normal number. You can keep it in its index form, and this is correct. So whenever you see an expression like this, 2 to the power of 3 or raised to the power of 4, remember the power law of indices, that the powers multiply and you have this. Now let's see why this power law is true. Let's take this 2 to the power of 3 as a given number. If I have 2 to the power of 3 or to the power of 4, according to indices that we've known, according to the concept of indices that we've known, this can be said to be 2 to power 3 times 2 to power 3 times 2 to power 3 times 2 to power 3. Remember, when you have a given number, say a to the power of 4, this is a times a times a times a. A multiplied itself 4 times. So let's look at this 2 to power 3 as a single number. Let's say it is raised to the power of 4. It is this number multiplying itself 4 times, which we've just written out here. Under the concept of multiplication law, we said when an index number multiplies itself, so when you have the same base multiplying, according to the law of the multiplication law of indices, that we add the powers. So all of these are the same base, so we take one base and add the power. So this will be 3 plus 3 plus 3 plus 3. And this will be 2 to the power of 3 plus 3 is 6, plus 3 9, plus 3 12. So this is 2 to power 12. And it corresponds with this. So the power law of indices is accurate that when you have a number, an index number based on another index, that the two powers multiply. The next law of indices we want to discuss is the zero index law. Now, we want to go through all the laws of indices so that when you start seeing various examples, various problems on indices, you can remember all these laws and resolve them. Okay, for the zero index law, if you have any number to the power of 0, that this is equal to 1. This is the zero index law. So any number at all, however the expression is, to the power of 0 is equal to 1. Even if I write something like a plus 2x over 2, as long as it is raised to the power 0, the answer is 1. Anything at all to the power of 0, the answer is 1. Let's look at a little proof on this concept that a to the power 0 is equal to 1. Now, if I have a number a divided by a, we know that this is definitely equal to 1. Any number divided by itself is 1. Okay? So, but let's look at the law of indices here. Now, if you write a number, let's say 2, the power automatically is 1. So, a written like this, the power is 1. Any number on its own, the natural power there is 1. This is raised to power 1, this is raised to power 1. Unless otherwise indicated that the power is negative 1 or any other power. But if there is no power written, the power is certainly 1. Now, so a divided by a we know is 1. But following the law of indices, this is a to power 1 over a to power 1. The power here is 1. And according to the law of indices division, that when the bases are the same, you subtract the power. So this is a 1 minus 1 because I'm subtracting the power. And this is a to power 0. So we can say that a to power 0 is equal to 1. And so the law of indices here, the zero index law, who says that any number raised to power 0 is equal to 1, holds, and it's true. Another law we want to consider is the negative index law. Now, the negative index law says that if I have a number raised to a negative index, that it is equal to 1 over a raised to power n, a raised to that index. Now, a raised to a negative index is equal to 1 over a raised to that index on the positive form, minus n, 1 over a raised to power n. This is the negative index law. And let's give a little proof to show that this is really true. Now, I'm going to prove this from the right hand side to see the left hand side. Now, from the right hand side, I have 1 over a to power n. Let me see if I can convert this, if I can prove this to be this. Okay, so if I have 1 upon a to the power of n, we can write this 1 rather as a to power 0. Remember, we just discussed the zero index law that a to the power of 0 is 1. Anything to power 0 is 1. So let's just replace this one as a to power 0 so it can also maintain the same base here. as a. Okay, so we have divided by a to power n. Now, the law of indices here is the division law of indices, because we have seen the division of two index number, and the division of indices says that if we have the same base and the index number are being divided, we take one of the base and subtract the powers, 0 minus n. And if we subtract this power here, this will be a. 0 minus n is a negative n, and this is the same as this. So we've been able to transform this to this. So definitely, when you have a to the power of negative n, it is equal to 1 over a to power n. This law holds. Let's look at some examples here. If I have a number, say 2 to the power negative 3, this is directly 1 over 2 to power 3. And it also means that if you are given an expression 1 over 2 to power 4, it is directly, you can convert this to 2 to power negative 4. So if the expression is given in this form, you should be able to translate to this form. If it's given in this form, you should also be able to translate to this form. We also have another law of indices here we want to consider, which is the fractional index law. Now, let's give a basic example of the fractional index law, and from there, step it a bit higher to other fractional index law. If I have an expression a to power 1 over n, a to power 1 over n, now this is equal to the nth root of a. Now, this is not the same as the negative index, where the negative index law, where we have 1 upon a to power n is equal to a raised to power n. This is not the same as this. This one is 1 over a to the power of n. This is just a to power 1 over n. This is the whole index. All right. So this and this are not the same. So if you have any expression a to any fractional index 1 upon n, it is equal to n root of a. So this denominator here, this is a fraction, a numerator and a denominator. This denominator automatically becomes the root value. So this is the nth root of a. Now, most times it's always a to the power here, to this one here, a to this power, to this numerator. Okay, but you know, a to the power 1 is still a. So we can just write nth root of a. Now, if we step this a bit higher and say a to the power n over n, we have an index like this, an index, the fraction m over n, a to the power of m over n. Just the same way, this n is the root, n becomes the root, the denominator becomes the root. We can have nth root of a to power n. So the numerator becomes the power of a, while the denominator becomes the root number. So this is the nth root of a to power n. Okay. Now we can also write this as or okay, n root of a all to the power of m. This and this are the same. So if I want to put the power, if I want to put this numerator as the whole power, is fine. If I want to put it just on the a, is fine. But know that the denominator is the root number, nth root of that number, nth root of this base. Okay, so this is the fractional index law. A to the power of m over n is equal to the nth root. The denominator is always the root number. Subject the denominator to the root number, and then the numerator is always the power on the base, or on the full root and the base. Let's look at a practical example. Let's say you have 16 to the power of 4 over 3, and we want to resolve it. We want to resolve this in the fractional index using the fractional index law. 3, which is denominator, becomes the root number, and this is 16 to the power of 4. We can also write this as 3 is the root number. This is 16 all to the power of 4. Whether you write it this way or this way, they are both correct. Either the power is inside the root, on the base, on top of the base, or the power is totally on everything here, it is correct. However you represent it. Now let me show you why this is correct here. Let me show you why this is correct. Let's do a little proof on this to explain that this and this are the same. Following this. So let's do a little proof here. If I have the expression or the index number a to the power of m over n, we can write this as a to the power of m times 1 upon n. We can split this m over n to be m times 1 over n, because m times 1 is m, all divided by n. So this is correct, right? Okay, so let's push this a little, following the power law of indices. From the power law of indices, we know that this can be written as a to power m all to power 1 over n, according to the power law of indices. That when you have a number to any index or to another index, that you can multiply the two index. You can multiply the indices to be this. So I can transform this to this, and this is correct, right? Okay. And from this fractional index law, the basic fractional index law, which I have a to the power of 1 over n to be this, we can write this as a number to this 1 over n is the nth root of a to the power of n. Remember, a number to the power 1 over n is nth root of that number. So a number to the power 1 over n is the nth root of this number. So we've gotten this first part. So this is correct. Right, now let's also look at another instance where we have m over n to be a to power. Now, multiplication is commutative, right? So I can actually write 1 over n times m. It's commutative in the sense that I can say this times this or this times this. They will still return back to m over n. Okay, if that is true, which it is, we can say this as still following the power law of indices, a to power 1 over n or to power m. On this, from this point, we are directly seeing a to power 1 over n, which is the nth root of a. This is the nth root of a from this. Sorry, nth root of a from this. Now, but it is raised to power m. So we can see this other side of the fractional index law, nth root of a all to the power of n. So this and this are all correct. So next time when you see a to power m over n, it is either the nth root of a to power m or the nth root of a all to the power of m. Any representation is correct. So either this or this can serve your purpose, and you simplify and get your final answer. The next law of indices we want to discuss is the product power law. The product power law. Let's say you have a product of numbers, let's say ab to the power of n. This is a product of two numbers to the power of n. The product power law says that each of these numbers can be raised to that power. So we have a to power n, b to power n. I can split this way, a to the power, b to the power. And I can also recompress this back to this. This is what we call the product power law. Even if you have a product of three numbers here, if I have a, b, c to power m, this is a to power m, b to power m, c to power m. Let's look at a very basic example on this. Let's look at a basic example on this. If I have an expression 2y to power, say, 3, this is a product of numbers, right, to a given index. This is 2 to power 3, y to power 3, and 2 to power 3 is 8, so this is 8y3. So this is how we resolve the product power law. When you have a product of numbers to a given index, each of the numbers can be raised to that power. You can simplify and have this. Let's also look at the quotient power law. Just like the product power law, we can also have the quotient power law. For example, where I have a over b to power n. instead of a times b to power n from the product power law, we can also have a over b to power n. The quotient, there's a quotient here, the division of number here to a given power. Each of this base number can be raised to that power. So I can simplify this as this and resolve. Right. So this is the quotient power law. Any example can also flow from here. However you want to write the example, we can take any practical example here. We can say, okay, let's look at a very vivid example. I can say 4 divided by 2 to power 2. Let's look at this very basic example. Now, we know that 4 divided by 2 is 2 to power 2. So 4 divided by 2 to power 2 is 2. 4 divided by 2 is 2 to power 2, which is 4. All right. So we can also use this quotient power law to simplify. So this can be 4 to power 2 over 2 to power 2, which is 4 to power 2 is 16. That is 4 times 4. 16 over 2 times 2 is 4. And 16 divided by 4 still gives you 4. And this holds. So it means the quotient power law is true. There are so many resolutions we can do with the laws of indices. Okay, so but in mathematics, the most important thing is always working with the simplest method. Because you want to give solution to problem and you want to give the solution fast, use a simple method that gives you the answer quickly. So if I have something like this, I would not want to resolve into this, I just want to simplify like this and get my answer. Okay, so this is the quotient power law. We can see that it holds. So far, we've discussed all the laws of indices. And with these laws of indices we've discussed, you'll be able to resolve any problem involving indices. Now, but I know you might be wondering, so far in our laws of indices, we didn't solve any expression, any example involving addition law of indices or subtraction law of indices. For example, if you have 2 to power 3 plus 2 to power 2. What we did was like multiplication law of indices, but we didn't do examples involving addition law of indices or subtraction law of indices. So what do we do when you have a problem like this? What do you do when you have a problem like this? There is no direct law of indices governing this. There's no direct law of indices governing this, or governing when you have a minus. There's no direct law of indices. But you can use your mathematical knowledge to know how to transform this. If I have a problem like this, I know that this is the same thing as 2 to power 3. Okay, 2 to power 2 times 2 to power 1. Now what I'm doing is, if I have a problem like this and they have the same base, I'm going to find a way to see the lower index number inside this. As long as they have the same denominator, I can always find this inside this. Because according to the law of indices, this times this is this. We take one of the base here, and then this plus this, which gives me back 3. All right, so 2 to power 2 times 2 to power 1 is 2. 2 plus 1, which is 2 to power 3. So I can factor, I can split this to be in this form because I'm seeing 2 here. So plus 2 to power 2. And the next thing I will do here is to factor out the common value here, which is 2 to power 2. When I factor it out here, I will have just 2 to power 1 plus 1. If I factor this out here, I have just 1. If I factor this out here, I'll have this remaining. Okay? Okay, so this gives me 2 to power 2 bracket 2 plus 1, which is 2 to power 2 bracket 3. So this to power this is 4 times 3, which is 12. I can keep it in this form. I can also evaluate to this form. So this is how we resolve this. So there is no direct law involving addition of index number, just like we have multiplication law of indices. We don't have addition law of indices directly, but we can use this concept to solve any problem involving addition of index number of the same base. The same thing applies to subtraction of index number of the same base. Just find a way to factor out the smaller index number and simplify to this form.